Hi everyone. Okay, we're going to learn about speed of reaction in this video. Okay, so there's 4 parts to the video. The first part will talk about how do we measure or calculate the speed of reaction. Second part, we're going to look at what does it take for a chemical reaction to occur. Third part, we're going to look at the factors that affect the speed of reaction. And the last, we're going to look at data and graphs. Okay, so that's part 4. Alright, so why is the speed of reaction important? Okay, because in some instances, we need the reaction to be very fast. For example, I want to blow up a block of flats, like what you see in the slide. Okay, I want it very fast, within seconds or minutes. Okay, it doesn't make sense if I were to wait for 1 year for the block of flats to be blown up, right? Or why do we want to slow down certain reaction? Because maybe I want my epok-epok to last maybe half a year. Okay, so it depends on our need, and we will change the factors that affect rate of reaction to address our needs. Okay, so now let's look at a case study. So I have beaker A and beaker B. I've prepared 2 cm magnesium ribbon, and I will add them to 100 cm³ of hydrochloric acid. So the difference between the two acids are the temperature. Okay, so beaker B has a higher temperature than beaker A. So if you look at the video that I'm going to show you now, alright, I've already heated beaker B, alright, the acid in beaker B to about 60 degrees Celsius. So now I'm going to add the magnesium ribbon at the same time to see which reaction will be faster. But how do I know which reaction is faster? So I want you to think about that, okay, while we wait for the reaction to complete. Alright? And next, how are we going to measure or quantify the speed of reaction? So now let's look. Okay, the reaction is complete. Woohoo! Alright. Now, which reaction was faster? Obviously, we can see it's beaker B. Why do we say it's beaker B? Because, number 1, magnesium ribbon, all the magnesium ribbon has completely reacted faster. So, completely reacted faster. So, I want you to write this down in your notes as well. Okay? First. Okay, so magnesium ribbon has completely reacted first. The second reason, I want you to look at the effervescence, the bubbles that was produced. If you look at the video again, you will see that beaker B has a larger or higher rate of effervescence produced. So more effervescence was produced in the same amount of time. More effervescence produced in the same amount of time. So oops. Okay. Now, so we want to look then we think about what causes the effervescence. So let me change my color of the pen. Okay. Oh, what's happening? Oh no. Change the color of the pen. Okay, so what caused the effervescence? Okay, now this was a metal plus acid will give me salt and hydrogen gas. So what caused the effervescence is most likely, obviously, the hydrogen gas. Okay, so the gas caused the effervescence. So how can we then quantify, okay, that B produced more gas in the same amount of time? So that's why we ask you, how can we measure the speed of reaction? So how can I measure the amount of gas produced? So think about that. If you want, I'll change the color. Okay. Oops. Oh no. Great. So, how to measure the amount of gas produced? So if you recall what you have been taught in Sec 3, you realize that there's a few ways you can measure and collect the gas produced. So measure and collect the gas produced. So I want you to try and recall what was that method or apparatus used. Okay. So you can recall it's actually the gas syringe, where you measure and collect the volume of gas produced. Okay. Now, other than volume of gas produced, what else can we measure? We can also measure the mass of gas produced. But how? Okay. So we can measure the mass of gas produced by looking at the loss of mass of the whole contents of the flask. Okay, so there's two ways. Number one, volume of gas produced. Number two, mass of gas produced. Alright, so now let's look at the first part, the first method, which is measuring speed of reaction from the volume of gas produced. So this is the first method. So it can be determined by collecting and measuring the volume of gas produced at irregular time intervals. So we take magnesium and hydrochloric again as an example. Okay, so as we said earlier, I can use a gas syringe, correct, to measure and collect gas. Okay, why can't I use other methods such as displacement of water or displacement of air? That's because you want to measure, you want to quantify the amount of gas or volume of gas produced. And these two methods, which is displacement of air and water, they don't really allow you to measure accurately. Okay, so how do I draw a gas syringe? So first of all, you need ruler, you need pencil, and you need to label. Okay, so use a ruler. Okay, I can't use a ruler here, so I'm drawing it freehand. Okay, but you should be using a ruler. Okay, first you draw the syringe, the body of the syringe. Next, you draw the piston. Okay, so this is the piston. So first is the syringe, next is the piston, last is the markings, the graduation. Okay, so this is important, your markings. Okay, now what else? We would want to also draw the retort stand. Okay, it's pretty simple to draw the retort stand. Okay, again, please use a ruler. Okay, it looks very weird. Let me draw it properly. Okay, so this is the retort stand. Eraser. Okay. Okay, so label retort stand. Okay, and we're done. Right, so this is how your diagram is supposed to look like. Remember, use a ruler, pencil, and label. Alright. Okay, next, results of experiment on graphs. So how does the data look like on a graph? So if you look at the graph, okay, it's not a straight line. Okay, it's a curve. Okay, first of all, it's a curve. Alright, and then at this point, you will see that the line goes straight. So now let's look at the three segments. So segment 1, this is segment 1, this is segment 2, and this is segment 3. Okay, so we're looking at the three segments. So in the first minute, about 17 cm³ of hydrogen gas was produced. Then if you look at the second segment, only 8 cm³ was produced. So what does it mean? It means that the gas produced initially was the largest. Not the largest, the most. Okay? Oops. Alright. So how do I know? And then, sorry. Now, if you look at the third part of the graph, you will see that the reaction has stopped. How do I know that the reaction has stopped? If you look at the graph, what is so special about this part of the graph? The gradient is actually equal to 0. Okay, and if you look at part 1 and part 2, the gradient at part 1 is actually more than the gradient at part 2. Okay, so in conclusion, we can say that the speed of the reaction is indicated by the gradient of the graph. So what does the graph tell us? Okay, so the shape of the graph tells us whether the speed of reaction changes or remains the same as time passes. If it remains the same, it will be a straight line. Okay, if it changes, you will see there is a curve. Like in this case, you will see there is a curve, whereas here it does not change because it's a straight line. Okay, the steeper the gradient, the faster the speed of reaction. Let me just erase this part for you. Okay, so the steeper the gradient, the faster the speed of reaction. Oops. Okay, the gradient at T2 is less steep than the gradient at T1. Okay, can you see? This gradient is less steep than this gradient. Okay, as the reaction proceeds, the curve becomes less steep. This means that the speed of reaction is decreasing. So as gradient decreases, the speed of reaction also decreases. Okay, let's look at this part of the graph where, okay, let me just erase everything here. Oops, okay, no. Okay, let's look at this part of the graph. Okay, this part of the graph, your gradient is equal to 0. That means reaction has stopped. So what caused the reaction to stop? Okay, so what caused it? Okay, so I want you to write this down in your notes as well. So what caused the reaction to stop? There's two things that causes the reaction to stop. Number one, your limiting reactant has been completely used up. Number two, an insoluble product has coated the reactant, preventing further reaction. Okay, so two ways where a reaction can stop. Number one, your limiting reactant is completely used up. Number two, your insoluble product that was formed has coated the reactant, preventing further reaction. Okay. Alright, so let's fill in the blank. Okay, a Watt gradient means that the rate of reaction is fast. So as we recall previously, when gradient is steep, reaction is fast. So a steep gradient means that the rate of reaction is fast. So a gentle gradient means that the rate of reaction is slow. Alright, so now let's look at the second method that we can use to calculate speed. The second method is using mass. Okay, so the speed of reaction can be determined by measuring the mass of the reaction mixture at regular time intervals. Now, how is this possible? Because the mass will change, the mass will decrease as the gas produced escapes from the flask. Gas has its own mass. So as the gas is produced, the mass comes off. Get it? Okay? Alright. So how do I measure the mass then? I can measure the mass by using an electronic balance. Okay? There's nowhere else. You're not going to use the, what do you call that? That judge thing. Okay, never mind. Delete this. Alright, now let's look at the reaction between calcium carbonate and hydrochloric acid. Okay, so this is SWC, correct? Keswick. Okay, so now let's look at the setup. So you have this cotton wool. This is what's special. Everything else is similar to the first method, okay, except for the cotton wool and the electronic balance. Okay, so what is the purpose of the cotton wool? That's the most important part about this diagram, this apparatus. The cotton wool is used to prevent acid spray. So what then is acid spray? Okay, now when the reaction is happening, if you look at the bottom, your gas is being produced. So what gas is being produced here? CO2. So as CO2 is produced, okay, the gas is trapped in the liquid and bubbles are formed. And as the bubbles reaches the surface, it will burst. And when it bursts, the acid will be sprayed out, as you can see in this diagram here. You see, this is an actual picture of a bubble bursting. You know, there's a lot of people, okay, who do this as a research. They take pictures of bubbles bursting. Fun, right? So you see all this liquid being sprayed. So that is what we call the acid spray. Alright, so why do we want to prevent acid spray? The reason why we don't want acid spray is because it will cause a loss in mass. Okay, oops, change color again. It will cause a loss in mass due to the drops of liquid sprayed out of the conical flask. Okay, so hence the cotton wool will absorb. It will stop the liquid from escaping. So liquid will not escape. But yet at the same time, because it's porous, it will allow the gas to escape, which is what we want. Alright, so as you can see, the graph looks slightly different from the volume of gas. Okay, one thing is the mass is decreasing, whereas for volume of gas, the volume is increasing. So the mass is decreasing, and please take note that it will never ever reach zero. Okay, because at this point, basically this is the mass of the excess reactant plus product plus the flask plus everything else. Okay, alright. So as you can see here also, it's the same principle. Steeper gradient will give me a faster speed of reaction. Okay, so how would you measure the speed of a reaction? So try to complete the formula. Our first method, which is to measure the volume of gas produced over time taken. The second method is to measure the loss in mass over time taken. Okay. And the third is basically to find out the quantity of product formed over time taken. So basically your formula will follow closely how we calculate speed in maths, which is speed is equal to distance over time. So instead of distance, we are looking at the quantity of product produced or the loss in mass of reactant. Okay, so now let's look at this. Okay, you have CaSWC and you're producing carbon dioxide, which means there's two methods: volume of gas produced and the mass of gas is the mass loss due to the gas produced, gas escaping, I mean. Alright, so if number one, you're measuring the volume of gas, carbon dioxide is the gas, formed at different time intervals, so this is possible. Checking the pH of the mixture, we'll come back to that. Next, measuring the mass of water. Is this even possible? Can you isolate water? So is it possible to isolate water and find the mass produced? Okay, perhaps not. Alright, but if any of you find a method, you can just approach one of your chemistry teachers and discuss the method with us. Lastly, measuring the decrease in mass of calcium carbonate and dilute hydrochloric acid. So this is our method 2, measuring the loss, decrease in mass of the reactants. Okay, so correct. So 1 and 4, answer is A. Now why is number 2 out? Because if you want to check the pH, you can only check the pH of perhaps hydrochloric acid, and hydrochloric acid is a pH 1. Okay, so calcium carbonate will react with hydrochloric acid. So you want to look at the word, the keyword. So now it's stopped. And if you refer to the previous part of the notes, okay, let me just show you which one I'm talking about. Here. Alright, if you look back at your notes, alright, there are two ways where a reaction can stop. Number one, your limiting reactant is completely used up. Number two, the insoluble product form has coated the reactant, preventing further reaction. So now let's look at our question again. Okay, question 3. So, is either my limiting reactant has been used up or an insoluble product was formed. So now let's look at zinc and sulfuric acid, Zn plus H2SO4. It will give me zinc sulfate plus hydrogen gas. Now, as we can recall, zinc sulfate is soluble. So that means option 2 is out. So why has it stopped? Because the limiting reactant has been used up. So now the issue is I need to find out which is my limiting reactant. So my limiting reactant, as you can see here, is actually sulfuric acid. Why? Because they said zinc is in excess. So your answer will be B.